Hello, it's Keith here, and this is lesson 56 of my 650 assembly programming tutorials. It's a platform-specific series, and we're looking at the Atari 800 or 5200 because they're basically the same system, and we can work between the two differences just with a few slight tweaks and some conditional compilation, conditional assembly that is. Now, what we're doing today is we're looking at the Mintile system. The Mintile system I wrote is a multi-platform software hardware tile map system that also simulates sprites using the same tile drawing code. You can see it here on the screen. We've got this sample little thing here. We've got one chibi code that is being moved by the player's joystick here, and one that's being controlled by the computer. And we have, if I find the fire button, there it is, we can scroll horizontally and we can flip the character. Now, Mintile supports X flip, so we can turn around. It doesn't support Y flip. That is coming in a later edition. Mintile was designed for a game called Chibi Fight, a little test game that I wrote on the Z80 systems, and that needed horizontal flipping, but it didn't need vertical, so that's not been coded in. Now, what I'm doing though later on is I'm working on a version called MaxTile, which is far enhanced and offers other functionality as well. But at this stage, that would have been too much to port. It would be more complex than I thought was necessary. So we're going to look at this simple example today. Now, here you can see it running in 4-color mode, but the program does actually work in 2-color mode as well. If we just go to our source code here. Now, at the start of the code, we've got this this expression here defining the 4-color symbol. Now, if I comment that out and I recompile, now parts of the code that define the screen mode and things, they will actually switch to the 2-color mode. And so you can see here we've got the thing working in 2-color mode, although we're still actually using the 4-color graphics. I've reprogrammed the XFlip code to handle that correctly for the 2-color mode, but I've not redone the graphics. So we're primarily focusing on 4 colors today. Now, the Mintile game engine is designed to work at 32 tiles across and 24 tiles down. That's 256 by 192 on most systems. Now, in 4-color mode, that wouldn't be very possible on this system, and so the way we've actually compensated for that is instead of using tiles that are 8 by 8 pixels, we're actually using 4 pixels by 8 pixels, 1 byte times 8 lines effectively. That's in 4-color mode. In 2-color mode, it is actually generally 8 by 8 pixels, but that gives a good trade-off of giving a nice looking square tile that will be compatible with the other systems because of the screen resolution. But that is something that I've kind of compromised on, if you will, in this case, changing the resolution of the tiles to keep the size of them the same and the screen size. Now, what we're not going to do today is we're not going to look at for the majority of this code relating to reading the joystick and the actual mathematical operations of moving the objects around the screen. We cover how the sprite drawing and the tilemap drawing multi-platform code works in the multi-platform Mintile series. There's a link to that on my website, and there's other tutorial videos that you can see. All we're going to look at today is the platform-specific code that actually does the job of drawing the tiles to the screen on this particular system, because the rest is all multi-platform. Now, when it comes to drawing a sprite or the tilemap to the screen, what we need is a start draw position. Now, if we're redrawing the entire tilemap, then we just start from the top left corner, and we define the start of screen memory with this screen base here. Now, rather strangely, it's at 2064 here. That is because of the display list here. That is the screen address that's defined here, and so that's why that is the start address here. Now, our actual program here starts at memory address 4000 or A000, so that's after the screen memory, so the screen actually appears before the program. But when we're drawing just the sprites are actually simulated using a miniature tile map, and so for in those cases we actually need to calculate the VRAM destination, and we've got a get screen pos function that does that for us. Now, like most of my modern programming, I'm working with coordinates in logical units, and one logical unit is 2 pixels. We're going to need to convert that to tiles though, because we're going to be working in tiles, so there's 4 logical units per tile. Now, here we're converting the X position from a number of logical units to a number of tiles, dividing it effectively by 4. And then what we're going to do is we're going to take the Y position and we're going to calculate that into a memory address for our screen. Now, basically, the screen is 40 bytes wide. So to multiply by 40, we're multiplying by 32 and then by 8, and we're adding the 2 together. That's what we're doing here. We're then adding the screen base, which is 2060. There's plus 4 there. The reason we're adding 4 is because we're centering the screen. Our screen is 32 bytes wide, but our screen is 40 bytes wide. And so by adding 4 bytes, we're centering that virtual graphical screen there. So this is calculating our VRAM destination. all of the drawing is actually done by two routines: do strip, which is the normal version, and do strip reverse, which is the X-flipped version. We'll look at do strip first. So the way that the multi-platform code works is it repeatedly calls this do strip routine for whatever object we're trying to draw. If we were trying to draw a sprite, it would be split up into strips, and each of those strips would be drawn from left to right. Even if the sprite is X-flipped, it will still draw from left to right. The source data, the tilemap and the bitmap data is flipped and then drawn to the screen. Okay, so what we're doing here is we are starting our draw. Now, throughout this routine, the X register will contain 0. We are loading in the first tile number here. BCS is BC is a 16-bit value in the 0 page, which is the address of the tilemap data. Now, the tilemap in Mintile is a single byte per tile, so we're limited to 0 to 255 tile numbers. 0 is a special case. In the case of the background tilemap, this is actually an unchanged tile. The tilemap for the background is actually a cache of changes, so a 0 is an unchanged part of the tilemap. For the sprites, it's actually a transparent part. You can see around the legs there is no tiles being drawn, and that is what the 0 does in that case. So we're loading our tile number in here into Y, and we're skipping over if it's empty. Now, what we're doing next is we're checking the value tile clear, which is pointed to in memory here. Now, if that is a 0, then we are doing nothing. But if it's a 1, we're going to write a 0 to the source tilemap. Now, it would be a 1 in the case if I was drawing the background, because it's a tile cache of changes, and so once we've drawn the change, we set it to 0 so we don't try and draw things again that don't need redrawing. It'd be a terrible waste of memory. One important thing I should point out with Mintile is it doesn't use a double buffer. The reason for that is on a lot of the 8-bit systems, using 2 screen buffers is far too expensive memory-wise. It may not even be possible on a limited number of systems, and so it's designed to work without a double buffer. And so one of the things to do that is making sure we're not drawing more than we need to the background, because otherwise it would make the screen flicker, the sprites flicker before we redrew them. Okay, so there we're zeroing the tilemap entry. When we get down to here, we've now got a tile number in Y that we want to actually draw to the screen. Now, what we need to do is we need to calculate the source of the pattern data that we're going to draw to the screen. So what we're effectively doing here is we're multiplying that value in Y by 8 bytes, so there's 1 byte per line, 8 lines, and then we're adding the DE entry in the 0 page, the DES entry rather, the 16-bit address of the pattern data. Now, the pattern data you can see just here now. Actually, it's the same as the C64 graphics data, so we're reusing it there. And so that is the source memory address, and we're loading that into HLS here, this 16-bit value here. Now, what we're going to do next is we're going to transfer the 8 bytes of our lines to the screen. Now, we're going to use Y as the VRAM destination offset, and we're going to use HLS as the source. We're using X here, but X is always 0, so we're effectively loading from the address in 0 page entry HLS here. So we're loading a byte from the source pattern data, writing it to the screen, and then we're moving down 1 line. Now, there's 40 bytes on a line, and so to move down 1 line, we add 40 to the offset. Now, the offset is in Y, so we're just adding 40 there, and we're then incrementing the pattern data source there, the L part. So this needs to be aligned to an 8-byte boundary because we're not incrementing the H part to save time. So we're transferred 1 byte there. We're transferring a second one, a third one, a fourth, and so on. And you can see each time here we're increasing the amount of the value in Y by 40. Now, when we get down to here, we've exceeded the limit of what the single Y register can contain. So we can do 40 times 6 because that's 240, but anything more than that is over 256. So we're now updating the H part and the L part there to effectively get an offset of 280, which is 7 lines down. Now we're then storing the final byte here, and then what we're doing here is we're effectively updating the source tilemap address. We're then incrementing the VRAM destination, moving across the screen by 1 tile. We've effectively reset the H part, and of course the Y part will be reset by the next time we rerun this routine. The IYL entry in the 0 page is the tile count. That's how many tiles there are in this strip, and so we're decreasing that and repeating if we have more tiles to draw. Okay, so that's how we draw the unflipped tiles. Now, what about when we want to X-flip the tiles? Now, one option, of course, would be to actually store a second version of all the tile pattern data. I didn't really think that was a good idea. Another option would be to flip the data in real time. However, that's very slow and so not really appropriate for any kind of action-based game. It might be okay for a text adventure, not for an action game though. So what we're going to do is we're going to define a lookup table to convert the data. Now we're using this at memory address 200 because that is spare on this system. So this is a 256 byte lookup table. The bottom byte starts from 00 in the address and it will go all the way up to 255, and we will store the equivalent flip byte for all 256 possible bytes that we might encounter in our pattern data. So here is the lookup table flipping calculation routine here. Now the address is being loaded into HL, but the offset is going to be in Y, and the offset is also going to be the effective source byte that we want to flip. Now in 4-color mode, we need to take the 2 bits that define the color and we need to shift them into the opposite horizontal position. In the 2-color mode, we just flip each of the bits to the opposite position in the destination byte. We then store the destination byte into HL offset by Y. The source was Y and the memory address offset is Y, and that is important later. We increment Y and we repeat until that goes over 255 back to 0. So we effectively calculate the flipped version of all 256 values. Now how do we use those? Well, the calling routine, the multi-platform code, will call doStrip_reverse for a horizontally flipped image that we want to draw, a simulated sprite in effect. So what we're doing here is we're loading the top byte of the lookup table into the 0-page B entry. BC is a pair that we will use. The C part will be the byte that we want to flip, and then we can load in the equivalent flip byte. Now from then on, it's basically for a while the same as we've seen. So here we are loading in a byte from the source tilemap. Here we're clearing it if required. Here we're calculating the pattern source, and then we're loading Y with 0 here for the offset to the VRAM destination. Now, like before, we're loading in the byte from the source pattern here, and then what we're doing is we're transferring that to C. Now B already contains the top byte of the lookup table address, and so now the lookup table is pointing, the BC pair is pointing to an address in the lookup table, and it's effectively the flipped equivalent of the value in the C 0-page entry here. So we're loading in that flipped equivalent and then writing it to the screen, and that has effectively X-flipped the data, and it's only taken 2 extra commands to do that, which is far faster than any kind of bit shifting. We're then increasing our VRAM destination by 1 line, increasing our HLS source by 1 byte, that's our source pattern data, and we're doing this again in exactly the same way as before, a full 8 times to do all the lines of our pattern. So that's transferred that tile to the screen. And then we're just repeating here in exactly the same way, moving this time backwards from right to left in the source tile map, and then moving across 1 tile. So say we're moving across from left to right, we're flipping the data for each pattern, and we're moving backwards through the source tile map to flip the order of the tiles as they're drawn to the screen. The mascot sprite here is actually a miniature tile map. It's a very small tile map that's drawn to the screen. That's how we're able to reuse the same code to do both jobs. Now personally, I find that using the tilemap code to do the simulated sprites isn't too bad graphically, and it's a very, very big time saver when it comes to coding this up. Because if I had a separate sprite routine and a separate tilemap routine, that would massively increase the amount of code, and this has been written on dozens of systems, and so that would become quite considerable. And also the sprite code might have other limitations that could be problematic, but by limiting to working in chunks of 8x8, most systems can work very easily within 8x8 blocks because of their screen memory or because of their tile maps, and often their hardware sprites as well. So it makes it a lot easier to work within such a small starting block and then building that into something more significant. Anyway, go to my website, download the source code and the build script and all that, and you're welcome to use it in any way you want. Thanks for watching, and goodbye.